In question 2 then we've got 2-methylbutane, which is this, reacting with bromine, and it tells you it makes a mixture of products. And some people just assumed that it substituted once, so they said, well, okay, we know you can get various isomers, but that's C5H12, so if it just substitutes once with bromine, we'll get C5H11Br plus HBr, and so they gave that as the answer to the question. But there are two important issues here. The first is that that's not necessarily going to be the answer, because we know that one of the complications with radical substitution is not only that it can substitute at different positions, but that it can substitute multiple times. And so if it just says that one subset of products had this particular composition, that might not be the one that's only substituted once. Secondly, when they give you a number like that, 52.9% bromine, you can't just ignore it and say, I don't need to know that. It's a really important point in these figuring out the structure from the data kind of questions, that you use all of the data. Even if you feel you don't need it, you've got to show that the numbers are consistent with the conclusion you've come to. So you can't just assume that that's the case, you've got to use the number. So we know that it's 52.9% bromine by mass, and it asks us to work out the molecular formula from that. We could actually do this algebraically, because if we put n bromines into there, where n could be 1 or 2 or 3 or whatever, we could write down that the molecular formula would then be C5H12 minus n, right, because that's C5H12, so if we put n bromines in place of hydrogens, we'll only have 12 minus n hydrogens and n bromines instead. So if that's our molecular formula, we could write down that the percentage of bromine is equal to, each bromine is 79.9, so it's 79.9 n is the mass of bromine, divided by the total mass, so we've got 5 carbons is 5 12s are 60, plus 12 minus n hydrogens, so that's 12 minus n, because each hydrogen is just 1, so plus 12 minus n, and then our 79.9 n's again, all of that times 100, and we know that that's equal to 52.9. So it's messy but not difficult to rearrange that and solve for n, and you get that n is equal to 1. However, many of you probably look at that and think, yeah, I just don't want to do that, that's just too much algebra. So fortunately you don't have to. The alternative though is just to say, right, well, if it's just one bromine, what do we get? And then just work out the percentage in the normal way. So just say, if it's C5H11Br, which would be a reasonable guess, you know, that it's likely that a significant chunk of your product would just have one bromine in there. So then the percentage Br is just equal to 79.9, because we've got one bromine over the total. So 5 12s are 60, plus 11 is 71, plus 79.9 times 100, and that works out indeed to be 52.9. So that confirms C5H11Br. Okay, so that's probably the sensible thing, is just to guess and confirm that that's the case. So then we're asked to draw the 4 isomers of that compound, so we now know there's C5H11Br, so just one bromine in there, and it says that we can get 4 isomers starting from that compound. So you've got to be really clear that the carbon skeleton has got to be that. You can't suddenly get rid of a branch or put an extra branch in or whatever. If that's the carbon skeleton you started with, that stays there. All you're doing is substituting a bromine onto it. So a good place to start would be to say, right, well, all 4 of them are going to be based on that. So you can draw the 4 skeletons down, and then just think, right, how can we put bromine onto that 4 different ways? So thing to do is be systematic. Start at one end. So let's start by putting the bromine at that end. So that's one isomer. And then move it along. So there's the second one. Here's the third one. Okay, there's one hydrogen there. Okay, because there's only 3 carbons bonded to that one in the middle, so there must be one hydrogen there, so that could be substituted. So that's our third isomer. And then you might be thinking, well, shouldn't there be 2 more? Because we could put the bromine either on this one or on this one. But hopefully you're getting the idea now that whether you put it there or there, it's the same thing. Because that's the CH3 and that's the CH3. They're both bonded to the same carbon, so it wouldn't make any difference whether you put the bromine on that one or that one. You would get the same compound. So we can draw this one or draw the other one, it's the same thing. But that's what you've got to watch out for, that you don't put one of the isomers down twice and consequently miss out one of the other ones. So those are our 4 isomers. Now each of these is now treated with aqueous sodium hydroxide. So hopefully you're learning your reactions, you recognise that and think, oh yeah, that's the substitution reaction of a haloalkane. OH minus goes in, Br minus comes out. If you don't recognise that reaction, that's where you've got to be at the point where you see something like that and you instantly know that's the reaction. If you learn them as you go along and keep practicing exercises like this, that will happen. And that's the key to becoming good at organic chemistry. So what it means is that each one of those will be converted into an alcohol where the Br has just been replaced with OH. So in other words, these will be our 4 compounds. But what it actually asks you for at this point are not these structures. This is just so that we all know what we're talking about here, but it actually asks you for the molecular formula. So we started with C5H11Br, so now we're going to have C5H11OH. But this is the classic thing that they try to trip you up with. That is not the molecular formula, because in the molecular formula all the hydrogens have to be lumped together. All the atoms of each element are lumped together, so that hydrogen has to be added into that one. So C5H12O is the molecular formula. So next it tells us that each of these compounds is then heated with aqueous acidic potassium dichromate under reflux. So prolonged heating, which means that if they can be oxidized, they get oxidized as far as it's possible to go. And that's important in terms of deciding what the products will be. So you need to learn this story, that primary alcohols, if you oxidize with aqueous acidic dichromate, get oxidized first to aldehydes, but if you want to stop at that point, you have to use the distillation technique. If you reflux, which is what you're doing here, you'll oxidize primary alcohols all the way through to the carboxylic acid stage. And so that's what's going to happen with this one, because it's a primary alcohol. You're going to get that. Okay, so the alcohol becomes COOH, and this one is also a primary alcohol, so you're going to get that. This one is a secondary alcohol, and secondary alcohols, remember, get oxidized to ketones, but then they stop. You can't oxidize them any further, so this one will get oxidized to the ketone, which is that. But this one is a tertiary alcohol, and those can't be oxidized at all by aqueous acidic dichromate. And so that's the answer to part C, that compound A1 is this one. Okay, because it's a tertiary alcohol. Meaning that the carbon with the OH, so this one, has 1, 2, 3 other carbons attached, and tertiary alcohols can't be oxidized by aqueous acidic potassium dichromate. Because remember that the way the oxidation works is that you have to take away this hydrogen and take away a hydrogen from the carbon it's attached to, and there is no hydrogen there. That's why it can't react. So it can't be oxidized by aqueous acidic potassium dichromate, and therefore that one is compound A1. Okay, so we've taken that one out of the picture now because we know that one is A1. So next you have to see what you can learn from infrared that might lead you towards at least identifying which one is which. And as always, the key is identifying clearly which bands are present and documenting them with reference to the datasheet. Okay, so the thing that you're going to expect to be there looking at the three structures is they all have C double bond O, a carbonyl group, so they should all have a carbonyl peak. That therefore doesn't help you work out which one is which, but you still have to mention it. It's really important. You still have to show that they do all have a carbonyl peak. And of course that's easy to spot. It's the big one there in the middle. But as always, you check, so you get your set square thing, and you say, right, there we go. There's 1820, and here's 1630. Okay, that's not very good, but you get the general idea. There's 1630. Oops. Okay, 1820, 1630, and that means that they all have C double bond O as expected. What's more important though is that two of them are carboxylic acids and one of them is a ketone. So we should be able to pick out the ketone because it won't have an OH peak. And when you look at the three, it's immediately obvious that these two have this big, broad carboxylic acid peak. Carboxylic acid OH goes from 2,500 to 3,300. So it's a huge, broad peak. Whereas this spectrum obviously doesn't have that. It's got this sharp peak around 3,000, which is the CHs, but it doesn't have the broad OH peak. So again, mark it on. So you go to about 2,500 and say, right, there we are, there's that end of it. And here's your 3,300, sort of here. And you say, right, 2,500 to 3,300 means that these two, top two, have carboxylic acid OH. Don't you say a carboxylic acid peak, because they want to know which specific bond it is. Have a carboxylic acid OH, 2,500 to 3,300 wave numbers. Okay, therefore this one stands out because you can see it doesn't have that broad peak there, nor does it have an alcohol OH, which would be here somewhere. So this one has no OH. So what does that tell you about the functional groups? Well, it tells you that these two are carboxylic acids. And it tells you that this one is, well, it could be an aldehyde or ketone. Lots of people said aldehyde or ketone. But of course it can't be an aldehyde because aldehydes would have been oxidized through to the carboxylic acid. So of the possibilities that you're left with, it has to be a ketone. So this one is the ketone. One thing I just wanted to mention while we're talking about these things is a number of people talked about the C single bond O peak. So if you look in your data sheet, it tells you that there is a C single bond O peak at 1,000 to 1,300 wave numbers. But if you look back at the introductory videos on infrared, it tells you at length about why that peak is useless. And it's useless because you almost always get peaks in that range because it's in the fingerprint region, and you almost always get peaks whether there's a C single bond O or not, because you, in the fingerprint, remember, most of the peaks come from cooperative vibrations of several bonds vibrating in some kind of orchestrated arrangement, and those particular vibrations, their wave numbers will just depend on what the particular molecule is, and quite often, nearly always actually, you get something in that range. So please do not use C single bondo. If you start trying to interpret structures using a peak in that region, you will go horribly wrong, because loads of compounds that don't contain C single bondo contain peaks in that region. So the bottom line is you must ignore that peak when you're trying to figure out what structures are, otherwise you'll be misled. Quite a lot of people talked about it, and so long as what you say about it is true, in other words, yes, carboxylic acids will have that peak because there is a single bond OH, so then that's fine, you're not going to lose marks. But the danger is that you're going to delude yourself and start looking for it, in situations where it's not there. So do not use C single bond O. Okay, so C2 then asks us explicitly the identity of compounds D2 and D1, so this is the spectrum of D2. So as we said, D2 is the ketone, in other words, it's that one. So that is the identity of D2. And D1 is therefore the alcohol that it's made from. Again, you've got to make sure you've read the question carefully. Some people went back and drew the structure of the bromoalkane, which is going back a further step in the chemical changes that have been done. But D1 was the alcohol that this is made from, so this was what you needed for that one. Okay, so that's D1, which is the alcohol that's oxidized to make the ketone. And then part 3 turns our attention to these two spectra, which must come from these two structures, and it points out that you really can't tell which is which from the peaks we've been able to identify, because obviously these are both carboxylic acids, they both have the broad OH, they both have the carbonyl peak, and everything else is uninterpretable, so you cannot tell which is which in the way that we've learnt to do. However, what you need to be aware of, and what part 3 is getting at, is that the fingerprint regions of these spectra are different. They certainly have some similarities, but they're not identical. And therefore, in principle, you can use those. But it's not enough to say that. Don't just say, oh, the fingerprints are different, so you could use that. You've got to say, well, yeah, but how would that tell you which one was which? So you've got to talk about the fact that there is a database, okay, and that you can match the spectrum, the whole spectrum. Fingerprint is what makes the difference, but you match the whole spectrum to a database, and so long as your compounds are in the database, you can therefore positively identify which one is which. Make sure you mention the database and the idea that the combination of peaks, particularly in the fingerprint region, is unique to that compound. That's why it's a useful method. So that leaves us in part E with these remaining two alcohols, which are B1 and C1, but we don't know which is which. But it now gives us these mass spectra. So infrared couldn't tell us except possibly by the database method, but maybe mass spec can, because you can see that although they have the same molecular ion peak, obviously because they're structural isomers, so they have the same MR, and therefore they both have the molecular ion peak at M/Z equal the MR, which is 88. So that doesn't help us, but the fragment pattern is very different for both. So maybe that can help us. And the thing that really sticks out in the spectrum of B1 is this peak at 43, which isn't prominent in the other one. So if we go looking for that one, with a bit of luck, that will tell us which one is which. Okay, so we do the usual thing, and we look at all the possible fragments. However, it may be that again, you don't need to do that, because if we're looking for 43, there's no point just chopping a methyl group off there, because that just takes 15 away, and 15 away from 88 is obviously not 43. So rather than go through systematically, you can save time by sort of saying, right, well, if that breaks there, that looks more likely to give you a fragment of that sort of size. So there's nothing wrong with being more systematic, but it's just about the time thing. So if it were to break there, these are the two possible fragments that you could get. Okay, so if it breaks there, the positive ion is either going to be this side, which is going to be CH3 CH CH3 plus. Okay, remember it's CH there, not CH2, because there's just the CH and then this bond, which is the one that's gone. So CH CH3 plus. If you add that lot up, 3 12s are 36, 39, 40, 41, 42, 43. So straight away that ticks the bill for a way to generate the 43 peak. This one gives you CH2, CH2, OH plus, which comes to 45. So we're not interested in that one, but the 43 peak is there. So all we really need to do now is to go to this structure and see whether this one can give us 43. So you can see it's C3H7 was the way we got it there, and you can see that you can't do that here because you've got 1, 2, 3 carbons, but in order to separate those 3 from the rest you'd have to break 2 bonds. So there is just no easy way to break off C3H7 from this structure, or if you broke off those 3 there, again you'd have to lose the OH and you'd have to lose that one. So you cannot generate it in that way. CH2OH there, if you broke this bond, adds up to 31, so that's no good, and basically there is no way. So for this one there is no easy way to get M over Z is 43. So based really just on that peak you can pretty much get the answer. Okay, so you say this one is therefore this structure, because the 43 comes from CH3, CH, CH3 plus. And this one is therefore the other structure, which couldn't give us the 43 peak. And just for completeness, I guess you ought to show that you can get the most prominent peak from this. The 57 peak is a loss of 31 from there, and 31 corresponds to CH2OH. Okay, so if we break it here, you can get CH2OH, which adds up to 31, or you can get this 4 carbon fragment, which would be CH3, CH2, CH, CH3 plus, and that indeed adds up to an M over Z of 57. Okay, so the most abundant fragment is successfully accounted for by that one. You can get 57 from this one as well, actually, if you break this bond, so that doesn't help you very much, but it is consistent at least with this one being B2. The 29 peak though, actually, which is the second most intense of the fragment peaks here, actually is useful, because you can see where that comes from. 29 is consistent with an ethyl group, CH3, CH2, so if this breaks here, you can get CH3, CH2 plus, which gives you an M over Z of 29. And there actually is no easy way to get 29 from that one, because if you break off CH2OH, that's 31, so that's too much at that end. And here you can break off a methyl group of 15, but because of that branch in the middle, you can't actually break off an ethyl group. So there is no way easily to get 29 from that one. So that again is consistent with B2 having this structure, because it can give you the 29, whereas that one can't. So that's kind of icing on the cake. The 43 the 43 peak got it for you anyway, but the 29 confirms it.